Hi, everyone. Thank you for being here. Like Benoit said, my name is Guillaume Raymond, and my MSc project is titled Constraints on Gold Endowment at the Augmitto-Bouzan segment, orogenic gold deposit from stable isotopes and 3D fluid flow modeling. So for those who assisted in my previous presentation, it's going to be quite similar since I've been mostly working on writing the past few months. The project is under the supervision of Professor Georges Baudouin and Professor Christophe Laflamme, and with the collaboration of the research associates, Benoit Canel and Christophe Schaffer. So we'd like to thank our project research and funding partners listed here. So our goal here at the Université Laval for the Metal Earth project is to bring a better understanding of the auriferous fluid systems. And the large-scale objective of the source to sink project, well, it says it in the name, is to investigate the source, the timing, and the sink of the mineralization. My work will be focused on the sink, which are the mechanisms related to gold endowment at the deposit scale. But what controls spatial variations of gold endowment? From the literature, we know that gold is precipitated generally to change. It's generally related to changes in fluid flow conditions. And stable isotopes such as oxygen, carbon, and hydrogen are powerful tools to monitor changes in the fluid's past conditions, such as temperature, fluid-rock interactions, or even fluid sources. So the objective of my work was to compare the variations of fluid circulation conditions between the endowed and less endowed area of a deposit using stable isotopes. So the study area we chose is the Augmitto-Bouzan segment in the Rouyn-Noranda in the Abitibi, which is an orogenical occurrence that covers a 12-kilometer long stretch along the Geological Lake Break, which has an important potential in terms of gold-bearing content. The choice of the study area is based on the irregular distribution of gold-bearing mineralization across the segment, which is the problematic of my work, and the important archive of core sample, as well as the well-constrained geology. The study area is located in the Neo-Archean Abitibi greenstone belt, which, like I said, covers a 12-kilometer stretch along the Geological Lake Deformation Zone, itself host of multiple orogenical deposits in the Abitibi. The study area is divided into 6 main blocks, which are Augmitto, Cinderella, Lac Gamble, Astoria, East Bay, and Bouzan. From Augmitto to Astoria, these are considered the gold endowed sectors. And from East Bay and Bouzan, these are considered the less endowed sectors, which I'm going to show you why in a few slides. But first, let's take a look at the geology of the area. So north of the study area, we encountered the submarine and mostly mafic units of the Blake River group. We then encounter in orange the sedimentary rocks, which are mostly Gerwalkies and conglomerates from the Timiskaming group. And in dark purple, we have the ultramafic and mafic protoliths of the Pichet group, which are now altered in carbonate, chloride, and talc schists. The Pichet group is the physical expression of the Geological Lake Deformation Zone in the area. But there's already some differences, geological differences between the endowed and less endowed areas on the field. We can see, for example, that the thickness of the Pichet group band decreases significantly towards the less endowed sector to the point where it's not even mappable anymore. The Pichet also goes from an east-west direction to a northeast-southwest direction. And there's also no more sedimentary basin north of the fault in the less endowed sector compared to the endowed one. The mineralization is mostly located into veins of quartz, carbonate, tourmaline stockworks within the Pichet group or in the southern contact between the Pichet and Timiskaming groups. And gold is found as free gold, visible and invisible gold inclusions, or even as gold in sulfide matrix, such as arsenopyrite, pyrite, and pyrrhotite. So before going into the methodology, I'd like to introduce you to the longitudinal section, which is across the Pichet group, and which shows the gold content of the area. So as you can see, from Augmitto to Astoria, we have several ore chutes with important gold contents. But as we progress towards East Bay and Bouzan, we can see there's almost a complete loss of mineralization, except this small patch here, which is kind of hard to see, of 5 grams per ton per meter of gold. So yeah, we sampled veins in associated host rocks within the lower Pichet, which is the main target for gold mineralization, which has the appropriate alteration. We try to follow a regular grid longitudinally and in depth within the endowed sector and less endowed sectors, but we also sampled areas with no significant gold content within the endowed sectors as a comparative standpoint. So afterwards, we established a paragenetic sequence to narrow down our selection of sample and identify the veins related to gold events. We then analyzed the quartz, tourmaline, and carbonates from those veins for their stable isotope signatures and observed spatial variations of those signatures. Using mineral pairs of minerals in equilibrium within veins, we could use them as geothermometers to compute the temperature and observe the spatial variations of such temperatures. And once the temperature was known, we could use equations to compute the stable isotope composition of the fluid and discriminate the sources. Once the stable isotope composition of the fluid is known, we then computed the fluid rock ratios, which help quantify fluid rock interactions using oxygen isotopes. We also produced a 3D fluid flow model of oxygen isotopes using the hydrogeosphere software. So let's get right into it. The quartz tourmaline geothermometer shows that the veins of this segment are in the typical range of temperature for orogenic gold deposits, but the segment isn't in isothermal system, as we can see that the temperature covers the whole range of temperature of orogenic gold deposits. We can see also that the vein minerals have higher delta weighting values than in Val-d'Or. Yeah. If we plot those values of temperature versus the depth, we can see that there's an important thermal gradient within the Pichet group of approximately 32 degrees Celsius per 100 meters. And I say only within the Pichet group because we had 2 other quartz tourmaline samples from other host rocks that do not fit into the thermal gradient. So this thermal gradient is likely associated with a mixing zone. So we would have advection of high temperature fluid at depth that would mix with a lower temperature pore fluid towards the surface. So once we add the temperature, we computed the isotopic composition of the fluid as to discriminate the sources. So looking at the oxygen isotopes, we have 2 N members, and the same can be said for the hydrogen isotopes. But for the oxygen isotopes, we see we have a high delta weighting and high temperature N member, which is likely metamorphic and plots into the typical metamorphic field of Shepard 1986. But we can see with cooling, it goes progressively towards an upper crystal fluid, which is likely Archean seawater that's been trapped in the rock's porosity. We can see the same trend as vein minerals as for the fluids, that the Augmitto-Bouzan has a higher delta 18 composition than in Val-d'Or, which, like Benoit just presented earlier, is probably due to 2 distinct sources of metamorphic fluids. Looking at the hydrogen composition, we can see a low delta D and high temperature N member, which is likely metamorphic. However, we cannot say that the other number is seawater, since it goes way beyond 0 per mil. So we interpreted those really high values as evidence of flash vaporization condensation cycle, so phase separation of the fluid, which would lead to high delta weighting values and wouldn't affect the delta or the delta D values, and wouldn't affect the delta weighting values that much. So we interpolated the delta weighting values across the property. This is a view into the Pichet group only, to see what was going on with the oxygen isotopes. And we can see that there are two main upwellings of high temperature and delta weighting metamorphic fluid in the Augmitto-Cinderella and in the Asturias blocks, which are themselves blocks of really high gold content, which leads us to think that gold appears associated with the metamorphic fluid, which is also consistent with multiple studies that said that gold is likely transported in metamorphic fluid in general. However, what's interesting here is that the less endowed sectors are characterized by lower delta weighting values, which is interpreted as a more important upper crystal fluid component. We then computed the fluid rock ratios, and we can see a similar trend. In general, the fluid rock ratios are pretty low for a main hydrothermal drain. But what's interesting here is the values decrease towards the less endowed sectors, except like two outliers, which is consistent with the lower delta 18 and temperature values. And they both likely reflect changes of fluid flow. So to investigate the fluid flow, we produced a 3D model using the hydrogeosphere software. So we created a lithological unit based on this geological map, but only for Archean units. The model is quite simple. We only have subvertical units just for simplicity. And we assign hydraulic properties on each unit for based on representative values for dominant rock types. So, for example, Timiskaming and Pontiac groups, we assigned sedimentary rocks and Greywalkies hydraulic properties. Pichet group was comatitic schist properties, and Blake River group was andesites or volcanic rock properties. So before modeling, we needed to find the appropriate boundary condition for the model. So we gave the model an infiltrating source of 10 per mil, which is the metamorphic source, and a pore fluid composition of 1 per mil, which is the upper crystal source. And the most appropriate boundary condition was in A, where the metamorphic source is released from the entire base of the model and drained out throughout the trace of the Cadillac-Larder Lake break towards the surface. It's also the same boundary condition that was used in Val d'Or in Baudouin et al. 2006. We also chose a vertical fluid flow. So afterwards, we needed to try to replicate those field observations, but throughout the model. So we tested multiple scenarios, and the most appropriate one was to add corridors of higher hydraulic conductivity or higher permeability in the sectors where we saw higher delta 18 values. So we gave hydraulic conductivity of 10 times higher than the surrounding rocks of the Pichet group. Those higher conductivity corridors likely reflect deformation-related pathways, such as, for example, preferential foliation planes or even fractures. So this is the model after 1,000 years, after 5,000 years, and after 10,000 years. Afterwards, the model doesn't fit too much the field observation. So to form the isotopic zonation, in short, we need a short-lived hydrothermal system. So, yeah. but we still don't really understand why there are lower delta 18 values in the less endowed sectors. So to investigate what was going on, we created two north-south cross-section across the property. So one in the endowed sector in A and one in the less endowed sector in B. We can see in both scenarios that a proportion of pore fluid is drawn into the fault during hydrothermalism. So what's going on in the endowed sector is that we have a larger tissue group, which is modeled at 70 meters wide. And the local zones of higher permeability altogether allow an important metamorphic fluid flow in general. And the low porosity of the sedimentary rocks that surround the Cadillac break leads to a low volume of poral upper crystal fluid that's incorporated into the system. So overall, we have still a gold-bearing metamorphic dominated system in these areas. In the less endowed sectors, on the other hand, we have a thinner Pichet group, which already leads to a less abundant metamorphic fluid flow. And the volcanic rocks north of the fault lead to a significant amount of poral upper crystal fluid that is drawn into the fault, which dilutes the original metamorphic fluid, and therefore the gold content. So in conclusions, from stable isotopes, we can say that we've noticed an important thermal gradient, which is likely associated with a mixing zone, which would be mixing of a deep-seated metamorphic fluid of high delta 18, low delta D, and high temperature, which would mix with an upper crystal fluid of low delta 18, delta D around 0 per mil, and low temperature. We saw also some upwellings of high temperature and delta 18 metamorphic fluid, which overlap with high gold content zone, which leads us to think that gold is transported in the metamorphic fluid. And sectors of low gold endowment are characterized by larger upper crystal component and lower fluid rock ratios. From the fluid flow modeling, we noticed high permeability corridors that are probably due to deformation-related pathways in the Augmitto and Cinderella and Astoria sectors, which allowed an important rise of gold-bearing metamorphic fluid. The more abundant metamorphic fluid in the endowed sector is mostly due to the larger Pichet group in the less porous surrounding rocks, and the diluted fluid in the less endowed sector is likely due to the thinner Pichet group in the more porous rocks to the north. And in general, dilution of the metamorphic fluid decreases the gold potential of the considered sector. Thank you for listening.
Thank you, Guillaume. We have time for questions if you want. Michi? No?
Questions can be also asked through the chat if you like.
Yeah. Okay. Sounds good.
Benoit, I couldn't find my my mute button. You know, why is the Pichet so thin through the Bouzan? Do you think it's been, you know, structurally attenuated?
Yeah, that's something I was thinking about too. Yeah, I think it might have been maybe a change of the way it was deformed, or maybe it was just like I don't know, like maybe the end of komatitic volcanism towards there. But I think it might have been most likely due to maybe the formation. But yeah, that's a good question for sure.
Do you think its absence, largely absence, could be related to the lack of gold mineralization in there?
But yeah, I think it reflects maybe lower deformation, which leads to lower preferential foliation planes for the metamorphic fluid to rise in this area. So yeah, I think it's an important I think that pichet in general is an important conduit for gold, for the gold bearing metamorphic fluid. So the fact that it's thinner, it definitely has a great importance on the gold content.
Okay, thanks very much.